Hello there. In this video we're going to discuss how to calculate the decimal representation for the square roots of positive integers. In particular, we're going to try and find out what is the decimal representation of the square root of 7 accurately to 4 decimal places, and then we'll follow up with another example just to make sure we know how to work through this algorithm. Alright, so the goal for this video is to find out the decimal representation for the square root of a number up to any number of decimal places for which you want. So we want to know what this is approximately equal to. Right? So the first thing we're going to do is set up our algorithm, and we're going to do this similarly to how we did it with the long division of positive integers. So we're going to write this as 0, 7, 0, 0, 0, 0, 0, 0, and 0, 0. The very first thing that you want to do in this algorithm is group your digits. So group digits in pairs, right? So 0, 7 is a pair, 0, 0 is a pair, 0, 0 is a pair, 0, 0 is a pair, and 0, 0 is a pair. So what we want in the end is a 4 decimal accuracy for this square root, which is why I have 4 pairs of zeros after 7. And it's very important that you group these digits from the decimal place. Therefore, you can't have 7, 0 as a group, 0, 0 as a group, and so on. That's not going to work. Okay? So the second thing that we need in order to start this algorithm is we need to find the maximum value of x in the set of integers such that x squared is less than or equal to this number that we have here. In this case is 7. So we know that 1 squared is equal to 1, 2 squared is 4, and 3 squared is equal to 9. Therefore, the greatest integer whose square is less than 7 is going to be equal to 2, right? So that is going to be where this is going to start. And what we're going to do is we're going to bring this 2 over, and you're going to see why that is going to be true in a moment. So as we know, 2 squared is equal to 4, and then we're going to subtract like we have before. Right, so that's going to be 3. And similar to the long division method, then we're going to bring down a group. Right, in this case, we're going to bring down 2 zeros. All right, so now this is where the fun begins. Right, so what we're going to do is we're going to take this number 2, right? So 2 plus the first digit of 2, which is 2, which is the same as 2 plus 2, which is equal to 4, right? So what we're going to do is we're going to put this little 4 over here for the time being, right? And we're going to see what we're going to do with this in a moment. So now we're going to do a little guessing game, right? We're going to be looking for a number that sort of goes in this little circle here, namely a digit. And that digit has to satisfy the following property. So 4 digit times that digit must be less than or equal to 300, where this 300 is coming from here, right? So for example, 45 times 5, 46 times 6, 49 times 9, and we want the greatest integer that makes that true. And one can find that that digit actually is equal to 6. So 46 times 6, one can find to be equal to 276, and then we're going to subtract to get 24, and then we're going to bring those digits of 0 down. Right, and let's bring that digit here since we found what that digit is. And what we're going to do is we're going to do 46 plus 6. So what we're doing is pretty much the same thing that we did before. So 2 plus the first digit of 2, so we're going to be doing 46 plus the first digit of 46, which is 6, which we know is going to be equal to 52. And that 52 is going to go over here. And now we're going to repeat the process. And keep in mind, this 6 that we found can go right up here. Alright, so let's find what this number is. So what do we want? So we want 520 something times something to be less than or equal to 2400, and we want the largest digit that makes that true. Right? So one can find that the largest digit is going to be 524 times 4. That is going to be the largest one that is less than or equal to 2400, which in this case is going to be 2096, with a difference of 304, and then we're going to bring down a set of zeros to give us 30,400. So again, our special number that we found is 4, and we can also put our 4 up here as well. So this stuff on the left-hand side is sort of like scratch work in order to sort of generate our decimal expansion. Okay, so we're going to repeat the process as we did before. So we're going to do 524 plus the first digit of 524, which is 4, which as we know is 528. So we're going to have our 528 number here, and then we're going to be looking for our next digit of the sequence. So we're going to have 5,280 something times something, and we want this to be less than or equal to 30,400. So notice that these numbers are going to get bigger and bigger on each iteration, and you can find that this next number in sequence is going to be 5. So one can find that 5285 times 5 is going to be equal to 26,425 with a difference of, let's see, what is that? That's going to be 3975, and then we're going to bring down another grouping of zeros. And this magic number 5 we can throw up here now, right? And now that we found our magic number, what we're going to do is we're going to add these numbers together. So 5285 plus its first digit is going to be 5290. So we're going to have 5290 and some digit. So again, we're going to do 5290 digit times that digit, and this must be less than or equal to 397500. Really big number. But again, you can find that this number is going to be equal to 7, right? And you can find that that number is 370349. Subtract, and actually we don't need to know what this is because we have found our fourth digit, right? So therefore, the square root of 7 is approximately equal to 2.6457, and if you want more digits, you can continue with this process. So now let us go through another example. So example 2, let's try and calculate the square root of 19. Alright, so we're going to start off with the same exact process. So we're going to have our little box here, and we're doing the square root of 19. So 19 has 2 digits, so that's fine. So we have 0, 0, 0, 0, 0, 0, and let's assume we want a 4 decimal digit accuracy. So we're going to have 4 sets of groupings of 0. So again, group in terms of 2. So if you're doing, say, the square root of 233, 0, 2 will be the first group that you have under this little box, right? So we're going to have our side work here and also some side work on the right-hand side, and our decimal digits are going to be right above. So again, we start off by finding the largest integer whose square is less than or equal to 19. As we know, 4 squared is 16, and 5 squared is equal to 25. So we're going to be starting with 4 as our number here. So 4 point something is where this iteration begins, right? And notice all these digits are the ones that go over. So we're going to do this number 4 plus its first digit, which is going to be 4, and 4 plus 4 is going to be 8, and then we're going to be looking for our next number in this sequence. So what do we want? So we want 8. So what is 4 times 4? 4 squared. 4 squared is equal to 16, and 19 minus 16 is 3. And then we're going to bring down our digit. So what we want in this next iteration is 80 something times something must be less than or equal to 300, and we want the largest number that makes that true. In this case, that is going to be 3. So we can find that 83 times 3 is going to be 249, right? So 3. And 300 minus 249 is going to be equal to 51, and then we bring down our next set of digits, right? So again, we have 83. 83 plus its first digit is going to be 86. So we're going to have 86 and then another digit, right? So what do we want? We want 860 something times something to be less than or equal to 5100. So one can find that that number is going to be equal to 5, right? So 865 times 5 we can find to be equal to 4,325 with a difference of 775. And then we're going to bring down some zeros here. Okay, so again, repeat the process. 865 plus its first digit is going to be 870, and then we're going to be looking for our next digit of this pattern. So we're going to have 870 digit times that digit must be less than or equal to 77,500. And again, one can find that that number, in this case, is 8. Right? So 8,708 times 8, you can find to be equal to 69,664 with a difference of 7,836. And as usual, we bring down our last set of digits. Okay? So we're going to do 8708 plus 8, which is going to be equal to 8716, and then we're going to be looking for our last digit of this. So we want this to be equal to what? So 8716 digit times digit must be less than or equal to 783600, right? 783,600, and one can find that that number is going to be equal to 8. Okay, and once you do that product, you're going to find that that's going to be equal to 697344, and then you subtract, but we actually do not need to know what this number is, but our next special digit is 8. Right? So therefore, what do we have? So we have that the square root of 19 is approximately equal to 4.3588. So this is a long division analogous algorithm that can be used to find the square root of any positive integer. If you're feeling very creative and explorative, maybe you can figure out how to do the cube roots in a very similar way. Hope you enjoyed. As always, if you enjoyed, please like this video, consider leaving a comment, and if you enjoy the channel content, please subscribe. We publish several new topics every single week. Thank you.